Shannon Myers, and today we'll be looking at a problem you'll see at the beginning of an intro differential equations class. Just taking a look at different types of solutions and initial conditions. So here we go. We want to verify that the one parameter family, y squared minus 2y equals x squared minus x plus c, is an implicit solution of the differential equation quantity 2y minus 2y prime equals 2x minus 1. So here we go. We're going to need to differentiate with respect to x quantity y squared minus 2y, and then we have to do the same thing on the other side, and we're differentiating that solution to see if it matches the differential equation that's underneath. So the left-hand side has y's in the terms, and we're differentiating with respect to x, so that's implicit differentiation. So you're going to remember that the derivative with respect to x of y is dy dx. So if you have y raised to a power, you use the chain rule. So continuing, we'll get 2y times y prime, or dy dx, minus 2 times y prime is equal to 2x minus 1 plus 0. Continuing, we will have 2y minus 2, I'm factoring out the y prime to the right side, equals 2x minus 1, and we verified that the DE is an implicit solution of the DE. Implicit because it's not written as y prime equals. All right, so now we want to find a member of the one parameter family in part A that satisfies the initial condition y at 0 equals 1. So here we go. With this guy, we are going to take a look at that original equation because this initial condition is in terms of y. And so applying that initial condition, I'm going to plug in a 1 wherever I see a y in the original equation. So I'll have 1 squared minus 2 times 1, and then a 0 wherever I see an x, because we want to solve for the unknown constant. So in this original equation, I'm plugging in a 1 wherever I saw the y, and I'm plugging in a 0 where I saw an x. So 1 minus 2 is negative 1, 0 minus 0 plus c is c. So c is equal to negative 1. And when I write that into the original, we'll have y squared minus 2y equals x squared minus x minus 1. All right, so for part C, we're asked to use our result from part B to find an explicit function or functions y equal to gamma at x that satisfies y at 0 equals 1. So when we do this, what we want to do is solve this equation that we have. And so I'm going to just get 0 on one side and everything else on the left side and see what happens. So we start with y squared minus 2y equals x squared minus x minus 1. Why don't we go ahead and complete this square on the left-hand side? So we'd have y squared minus 2y, and to complete the square, you add half of the coefficient of the y to the 1 term, and then you square it. So you're going to have to do the same thing on both sides. So we would end up getting x squared minus x minus 1, and then I'm adding negative 1 squared, which will just be 1. So those 1s are going to 0 out. So this is going to give us y minus 1, the quantity squared, is equal to, so the 1s, the negative 1 and the positive 1 will 0 out, and so we'll end up having, I'll just write it as x times x minus 1 because that's how x squared minus x factors. And then if you square root both sides, we will get that y minus 1 will be plus or minus the square root of x times x minus 1. And isolating y, we'll get 1 plus or minus the square root of x times x minus 1. So that is an explicit, these are two explicit functions. So I'll put it in roster notation. We would have 1 minus root x times x minus 1, comma, 1 plus root x times x minus 1 to get our two explicit functions, or yes, explicit functions for y. All right, so now let's take a look at the domain of these, the function gamma, all right? So basically, you have to be careful because the domain is the domain of a differential equation. The solution to a differential equation is different than the domain of the original function. So the domain of the function is going to have, both sides. So here, when we get a 0, to find the domain, we need to take a look at what happens when x, is undefined. So here we need to have x times x minus 1 has to be greater than or equal to 0. So you either get that x has to be greater than 1. We could graph this if you want to look at it. Or what's going to happen if you've got x between 0 and 1, what's going to happen is it'll be a fraction that ends up being negative in the parentheses x minus 1. So that one would not work because you'd get a negative under the radical. So when we take a look at x has to be greater than 0 or x has to be greater than 1, we have to take a look at between 0 and 1, and between 0 and 1 is not going to work, okay? Now let's take a look. So I'm kind of thinking of this in intervals. And so we have minus infinity to 0. We have 0 to 1. And we have 1 to infinity, right? So if x is greater than 1, we're all good. We end up with a positive number. If x is between 0 and 1, we just figured out we end up with a negative number. And if x is negative, right, we would end up with a positive times a positive, which is positive. So we're good to go, all right? Now, let's take a look. So this is, these are the values of interest, 0 and 1. And when x equals 1, are we good? Yes, because it's not in a denominator and the radical would be 0. When x equals 0, we're also good because 0 times negative 1 is 0. So it'll be inclusive. So the domain of the function gamma will end up being minus infinity to 0. The 0 is inclusive, union 1 inclusive, to infinity non-inclusive. Now, is y equal to gamma at x a solution to the initial value problem? Well, let's see. Let's take a look at the picture of the graph, and then you can verify the intervals and check that out. So if we let y1 equal to 1 minus the square root of x times quantity x minus 1, and then y2 would equal to 1 plus the square root of quantity x times, or x times quantity x minus 1. And if we graph, let's see what we have. So taking a look at the picture of this graph, you can see that it's got vertical points of vertical tangency at x is 0 and x is 1. So it's not differentiable there, so thus there wouldn't be a solution of a differential equation at x equal to 0 or at x equal to 1. And since x equal to 0 is the initial condition for the initial value problem, then there would not be a solution. So we would say no, since gamma at x isn't differentiable at x is 0. Hope you're having a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, click like and subscribe.